Okay, so today we're gonna continue with section 14.3 and we're gonna finish it. Continue. Okay. So here come number 4. Derivative at slope of tangent line. Begin from calculus 1, right? Just a little review here. Calculus 1. So we know that x, y. Let's say that we have a function fx. Then the derivative at the point x naught, y naught, f prime x naught, it will be the slope of the tangent line. And slope of the tangent line is limit h go to 0. F x naught plus h minus f x naught over x h. And it is the same as the limit x go to x sub 0 of fx minus f x naught over x minus x naught. So that's what we learned from calculus 1. So in this class, I apply pretty much the same thing. It's just that we have to deal with the surfaces. So in this class, we have a surface. So let's go. The glorified surface. Oh, here come. This is the surface here. That is the surface. Okay, so what do we want is that we want to figure out what is f sub x. It's the at a point x naught, y naught. So let's just pick that point here. X naught, y naught. Yeah, what would be this one? What is that? The partial derivative. So when we do fx, right, what happened is that we treat y as the constant. That is, let y equal y sub 0. This is a plane. Okay, so I'm gonna let y equal y sub 0. We're gonna get a plane. So let's sketch up this plane right here. Don't have to overkill yourself, right? Make sure that it's the plane. Okay, plane y equal y sub 0. We get fx y sub 0. This g of x there, right? Because we treat y as a constant. So gx, what is it? Is a curve on the surface. A curve on the surface is the trace. A lot of people call trace on the surface. Okay, let's do this trace right here. Huh? It's the trace right here. It's trace gx equal fx y sub 0. Okay, so we want to figure out exactly what is the partial derivative at the point x naught y naught. So you got to move up. So this x naught y naught right here. Huh? You have to go up here. You get this point. Well, if you take a look, the partial derivative is just going to be the derivative is the g prime x. So, oh my God, look at this one here. Huh? Notice that g prime x naught, this is the same as fx x naught y naught. Oh, should we know this one because we did it from calculus 1. It's just the slope of the tangent line to the trace gx equal fx y 0. It's on the surface, but it's also on the plane. On the plane. Y equal y sub 0. Yeah. So it is gonna be parallel to the x-axis. Oh my God. The tangent line is parallel to the x-axis. That is exactly what is the geometry of a partial derivative, right? Just slope of tangent line. It depending on whether you do a partial derivative with respect to x. If it's with respect to x, then that tangent line is going to be parallel to the x-axis. If it's with respect to y, then it's going to be parallel to the y-axis. Right? We're going to be using this formula to get the equation of the tangent plane. Right? Because you know we have the tangent line here. Right? When we have two tangent line, it will create a tangent plane. So we need to do more. So slope of tangent line is the limit h go to 0. Right? Well, because we treat y as the constant, it's going to be a fx naught plus hy minus fx naught y naught over h. Right? So then gonna replace this by x go to x naught. Okay, so we're gonna have fxy minus fx naught y naught, x go to x naught, x minus x naught, and this would be approximately fxy is z minus z naught over x minus x naught. Hopefully you see the geometry of a partial derivative, right? It's very cool. Derivative as rate of changes. Because they have two derivatives, so rates. Okay, let's do example here. Example, I have two of them. A person body mass index BMI is I equal W over H square, where W is the body weight, in kilogram, H is body height in meter, and phi partial with respect to H of I. For a young man, would W equal to 64 kilogram and H equal 1.8 meter, and interpret the answer. Okay, so once you do this, you see that, oh yeah, derivative is, of course, rate of change. Okay, ready? I'm going to do this one, and then I'm going to have another example. You can do the other example, because most of you are going to graduate from university, and of course, you're going to be working for a company, right? Rarely, 1 out of a million. You graduate from university, then you go to grad school, and you say, oh my God, I can do something much better than continue my education at grad school. And you begin to start your own company. It's like Facebook, Google, those guys back then. Rarely. Most going to be working for companies. Okay. Partial derivative with respect to the height of the body mass index, and that would be, well, if you want to have another notation, it looks like this. Take the partial derivative with respect to height of W over H square. So remember, you take the partial derivative with respect to H, right? You treat W as the constant, meaning that I'm going to do a partial derivative with respect to H. It's WH minus 2. Oh, it's make my life much better. So from here, we see that we got a W, right? And then minus 2H, negative 3. Okay, so that is minus 2 W over H to the power 3. Next, we want to figure out exactly what is going on when W equals 64 kilogram and H equal to 1.8 meter. So at W equal 64 kilogram, H equal 1.8 meter. The partial derivative of the body mass index with respect to height is -2 and then times 64 over 1.68 to the power 3. So if you do this, you're going to get a number is approximately -27. So what does this mean? It means that -27 over 1. The -27 here is the body mass index, and then the number 1 here is the height, is the meter. Well, but a person cannot grow by 1 meter, so we got to convert it to centimeter. So when we convert to centimeter, then it's gonna become a little more manageable. So it's going to -0.27 over 1. It's 1 centimeter, -0.27 BMI. From here, we should be able to interpret the weight remain unchanged. So that's the assumption. As the young man height increases by 1 centimeter, his BMI score decreases by 0.27. In another word, you want to say that the young man is getting taller and skinnier. That is what happened in this problem. I have a student a few years ago, and he was able to transfer to UC Berkeley. During a New Year festival, I went to Vietnam Town in San Jose, and I saw my student and said, "Oh my God, look at what UC Berkeley done to you, man. Because you look exactly like a problem that I just went over in class a few weeks ago." Yeah. And he said, "Hi, professor, how are you doing?" His voice was pretty weak. I said, "Dang, man. When you were in my class, you look much better. Right now, you look like a walking skeleton, dude. How was life in UC Berkeley? Are you gonna survive another year?" The undergraduate level, the last 2 years is very heavy, very rigorous. He only has about 4 to 5 hours of sleep each night. It's just like he has a new baby. Here comes the second problem. Manufacturing company used the Cobb-Douglas production model. To model their production level. Their productivity. Here comes the model, right? The Cobb-Douglas model. There's the model here. Fxy equal Kx and ym, where x equal number of worker, y equal number of capital. I'm going to say unit of capital itself better. Units of capital. K and M greater than 0 and N plus M equal 1. This is the model that is widely used in many manufacturing companies. A manufacturing company has modeled their productivity using this model. I'm gonna input the model here. fxy equal 10x 0.2 y 0.8 to model their production level. At the current x equal 100 and y equal 50. Should the company increase labor or capital to achieve the greatest increase in production level? Increased labor gonna lead to an increase in production level. So from here, right, we get a change in production level over change in labor. Change in production level is partial F partial X. Oh, sure. That means we are taking the partial derivative of function F. Yeah. So this is what we're gonna be doing here. So that is the partial derivative of 10 x 0.2 y 0.8. Gonna get a 2x negative 0.8 y 0.8 and then add into a partial f over partial x at 150, so it can be 2 times 100 negative 0.8 50 0.8, and that would equal to 1.1487. 1.1487. Okay. Similarly, change in production level over change in capital. Partial f over partial y. So that is just the partial derivative with respect to y of f, and that would be partial derivative with respect to y, 10 x 0.2, y 0.8. Right? We're gonna have a 8 x 0.2, y to the negative 0.2. And then we're gonna evaluate this at 150, 8, 100, 0.2, 50, negative 0.2. And this would give us 9.1896. So based on here, yeah, it would be better to increase the capital than labor.